I'm waiting for it to connect, and I don't see it connecting. There we go. All right. Welcome to Climate Chat. I am your host, Dan Miller, and today we have Peter Gleick, who's a returning guest, but last time he was on, it was on just Clubhouse only back then in October of 2022, so it's been quite a while, and Peter's been busy working on new things and a new book, and so much has happened to water and climate in the meantime, even in that short period of time, that we're really looking forward to catching up with Peter again on everything. And before we start out, Peter, I'd like you to, first of all, to welcome you, and also for you to give us a little bit of your background. How did you get focused on water and climate and those kinds of things?
Okay, well, hi Dan, thanks for having me on. It's great to be back. So I'm a climate and water scientist by training. I've been working on these issues for many years. I helped start the Pacific Institute in Oakland in 1987, which is an independent nonprofit working on global freshwater issues. And I'm a climate scientist in particular, looking at the impacts of climate change on water systems. And I got interested in them really back in the 80s, in part because climate change even then was already pretty clearly going to be a reality. We had a good sense already of the science. And I tied it in with my interest in water resources, again, partly because in the 1980s, we hadn't done much work. We, the global science community, hadn't done much work on how climate change might affect water resources, coupled with the fact that water is connected to everything we care about, as of course is climate. And it gave me the opportunity to look at human health issues and ecosystem issues and politics and economics and just a broad range of things. And that's what I've been doing ever since.
Very good. So your recent book, The 3 Ages of Water, covers really, I guess, all aspects of water beyond just climate change. So maybe you could just give us a brief overview of that book, because we're going to focus on climate impacts to water, but just so everyone knows what's covered in your book.
Yeah, so the book, it's called The 3 Ages of Water, Prehistoric Past, Imperiled Present, and a Hope for the Future. And in a sense, it's the human history of water, although it goes all the way back. The first age I describe as basically from the creation of the universe, the Big Bang, and when we had the first molecules of oxygen and hydrogen. And once we had oxygen and hydrogen, we had water. And then the formation of our solar system and where our water came from. The first empires and their dependence on water, they formed around the Tigris and the Euphrates River in Mesopotamia and the great rivers of China. And the role that water played in our early history. And that's the first age of water. And the second age I describe as really our age, when we created the technological tools and we understood what water was, and we figured out what water-related diseases were, and we built the infrastructure to manage our water demands. And that age, which is our age, brought great benefits to us, but it also brought what I describe as today's water crises, the failure to provide safe water to everyone, the impacts of climate change on water, impacts on our ecosystems, violent conflicts over water. And I argue that the second age is coming to an end, and that we need a third age of water, which I describe as a possible, I actually think it's likely, positive future where we can solve our problems. And I talk about how we could do that. I don't say that we're going to, I say that we could.
Right.
And I offer basically a hope for the future for moving to more sustainable water management and use.
Very good. Well, let's focus on, I guess, the current age and maybe the possible future age as well. And one of the big impacts on water, of course, is climate change. And I've made my own list, but I realize I should ask you, what are the major impacts of climate change on water?
Well, so water, of course, is connected to everything we care about, and intimately connected to the climate. The hydrologic cycle that, of course, you remember from second grade is evaporation from the land and from seas, and water goes into the atmosphere and forms clouds. Eventually, it precipitates back out as rain or snow on the land or on the oceans, and what falls on the land runs off back into the oceans, and that's the hydrologic cycle, and that's the climate cycle as well. And as the climate changes, and we know humans are changing the climate. Every aspect of the hydrologic cycle is being affected and will continue to be affected. Higher temperatures means more evaporation. More evaporation means more water in the atmosphere. More water in the atmosphere means more precipitation, but it also means more intense storms, both flooding and severe events on the other end of the spectrum, that is droughts. Rising sea levels affects coastal aquifers and ecosystems, and rising seas contaminate with salt coastal freshwater aquifers. We're already seeing that.
Correct.
We know that hurricanes are stronger. It's dumping more water on land, and it's causing more damage. Basically, every aspect of the climate that we can think about is connected to the hydrologic cycle. Ice loss is a key part of the hydrologic cycle. And of course, climate change is affecting ice everywhere, in the Arctic,
Right.
on ice on land, in glaciers, in Greenland and Antarctica. So we can expect to see, and we are already seeing, big impacts on water resources.
Okay, I think a little glitch in there, but let's start off with sea level rise. Jim Hansen has been saying that for the West Antarctic ice sheet, and because of AMOC and things like that, we might have a faster melting of Antarctica than everyone thinks. So we could have several meters, 10 feet plus, of sea level rise this century or shortly thereafter. What's your thoughts on where we might be in 100 years when it comes to sea level rise?
Well, sea level rise isn't my expertise. What I know about sea level rise comes from the scientific research that I read, that you also read, that probably your audience reads. And there's a lot of uncertainty about the rate of sea level rise and how fast it will happen. At the slow end, we're still likely to see a meter of sea level rise by the end of this century, which by itself would be catastrophic. But if the more extreme estimates are accurate, if the West Antarctic ice sheet melts faster, if Greenland melts faster, you could have meters of sea level rise, and that would truly be catastrophic. That would be devastating to the global economy and to ecosystems, and I mean, it's almost unimaginable. But again, even the low estimates are going to be really damaging. We've had 10 inches or so of sea level rise in the last 100 years, and already the storms that hit the coasts are more damaging than they would otherwise be. Even 10 inches is causing problems for us.
That's right. Will be a biggie, as they say.
Yeah.
And I think a meter is like the
one
low
of many
end.
biggies.
Meter is a low end estimate at this point, I think. So one thing about climate change, as the globe warms, people probably have heard before, for every degree Celsius of increase in average global temperature, you get an average of 7% more water vapor. We're about 1.5 degrees, so we're about 10% more water vapor. Doesn't sound like that much. Hey, 10% more, but it doesn't just end up being each rainfall is 10% more rain. Could you describe what's been happening already to for things like extreme rainfall?
Yeah, so that's actually a very good rule of thumb. For every degree Celsius, we get about 7% more water in the atmosphere. And as you say, it's above that already. And 10% or so is a big deal. It's a huge perturbation from the climates of the past, the climate that we've adapted to, the climate that we've built for. And so we're already seeing more intense rainfall in certain places. It doesn't mean that the rain everywhere is going to go up by 10%. What's happening is that wet areas are getting wetter and dry areas are getting drier. It's sort of the opposite of what we would want, because of the way the climate distributes water around the planet. It's unevenly distributed. So in the northeastern part of the US, for example, extreme precipitation has gone up quite a bit in the last couple of decades. We're getting more intense rain events. Not necessarily more rain events, but each rain event itself is more intense. And that, of course, again, is the opposite of what we want. It leads to more flooding. And we're getting at the other extreme, more droughts. The dry areas seem to be getting drier. California, the southwestern United States, has seen mega droughts of the kinds we haven't seen in the paleoclimate record for hundreds or even hundreds of years or longer. And so, again, it's not the averages that we have to worry about. It's always the extremes. And for water, that's especially true.
Yeah, and that's something I think a very important rule. That's an important rule of thumb. It's not the averages; it's the extremes, and that's true for temperature and other
Right.
things as well.
Right.
Well, let's stay on the West for a while. The West gets a lot of its water from the Colorado River, and people have been watching the dam levels drop, getting close to the intake valves of in the Colorado. Where do you see that? How do you see that playing out over the next? I don't know. Well, just over this century.
So interestingly enough, together with the Pacific Institute, we did an analysis, the very first comprehensive assessment of how climate change would affect the Colorado River. Back in, I think it was 1989 or 1990. We did it for the EPA together with the Bureau of Reclamation, which manages the big reservoirs on the Colorado River. And we integrated a model that runs the Colorado River that they use to allocate water, together with global climate models, with Jim Hansen's model from Geophysical Fluid Dynamics Lab in New York, the GFDL model at Princeton. I'm sorry, the Goddard Institute Space Studies model in New York, the Geophysical Fluid Dynamics Lab in Princeton, the NCAR model in Boulder, Colorado. And we looked at scenarios of climate change. And what we found was that rising temperatures alone would very dramatically reduce the amount of water available on the Colorado River because of evaporation and more demand for water out of the river. And there was uncertainty at the time about what would happen to precipitation. We looked at increases in precipitation, decreases in precipitation. One of the results all the way back then was that just to overcome the rising temperature, to hold runoff the same as historical average, precipitation would have to go up 20% in the basin. And it turns out it's not going up 20% in the basin. Precipitation's still about average in the basin, but temperatures have gone up and the flows of the Colorado were going down. And the Colorado is shared by 7 states in the US and Mexico. We actually have a treaty with Mexico that allocates part of the flows to Mexico. And those agreements among the 7 states and between the US and Mexico gave away more water than is actually available in the Colorado River. And that's the political crisis we now see on the Colorado. How do we deal with our inability to meet legal commitments? How do we deal with the shortages based on the demands that we assumed, the supply that we assumed would be available, and the demands that are imposed on that system that can no longer be met? That problem's going to get worse.
Well, I was going to say, yeah, I mean, that's the way it is now, and it's getting to be a crisis. But I assume you see this continued drop happening over the coming decades, right? We're to the point where it's going to be an extreme crisis, right?
Yeah. So the projections are that the Colorado River flows will continue to drop,
right?
And you can't magically make more water. It's a renewable system. It rains and snows every winter, and there's flows in the Colorado. But once you use the entire flow of the Colorado, which we do, except in really, really wet years, which we rarely see anymore, you can't have any more. And so the fight right now, the political fight, is how to allocate the shortages. Who's going to get shorted? And that's a political question, and it has to do with water rights. It has to do with state and local politics. It has to do with federal politics because the federal government manages the system. It has to do with international politics between the US and Mexico. It's in some ways an example of what's going to be happening around the world with big rivers as climate change affects water availability. It's going to affect who has water, who has access to water. It's going to affect ultimately conflicts over water.
Well, actually, speaking of that, my understanding is that Cape Town, South Africa, and Atlanta, Georgia, both came very close to running out of water. Is there a name for that when you run out of water for your city?
So the Cape Town example a few years ago, it's a very severe drought. They called it day zero.
Day zero, right?
It was the day when the municipal water system would literally run dry. The reservoirs were very low, when they would simply be unable to put more water into the pipes. And the fear was that day zero would come. The city of Cape Town implemented a whole series of very strict conservation and water restrictions in order to try and extend the limited supply that they had in the hopes that the rainy season would start. And they avoided day zero by maybe a few weeks. The rains finally came and they avoided it. But Atlanta, Georgia, Sao Paulo, Brazil, big cities are increasingly experiencing these more severe droughts, more severe than their water systems were designed for, and they're going to have to figure out how to manage those crises.
And well, but speaking of that, when do you expect the first major city to actually run out? Because they came really close, and but it didn't happen that time. But when do you expect it actually to be a major crisis for a major city to actually not have enough water?
So I can't answer that, in part because it depends on how the climate reacts and the weather and how local cities respond and what their water supplies are. It could be next year, could be this year, could be 10 years from now.
Okay.
Part of the issue is there is a growing awareness of the threat of climate change for water resources. And many water agencies that are smart are beginning to understand that that's a threat. And they're beginning to integrate climate model results with their own water systems and to run scenarios for what that might mean. And they're beginning to build what we call resilience to try and extend their supplies, to reduce their demand, to find alternative sources of water that might be available in the event of a crisis, precisely because no city wants to run out of water. That would be an economic and a human health catastrophe. But there are plenty of places around the world where already cities are on the edge, where they're already facing limited or scarce water supplies, outgrowing their local systems. And I think that's where we're going to see the crisis first. It'll be in some of the less developed regions of the world where water systems are already marginal.
I see. Well, and continuing on that, that's maybe because of rainfall patterns, but there are some major countries on Earth, including India and China, that rely on water coming from glaciers in the Himalayas. And climate change is affecting those glaciers. What do you see happening in that situation over this century?
So there's been a lot of discussion about that. A little bit of hyperbole, but also some disturbing reality. I was actually on a National Academy of Sciences committee that looked at the impacts of climate change on the Himalayas. Every city has a mix of different water supplies, and you're absolutely correct. Many of the big cities in many of the countries in Southern Asia, Vietnam, Cambodia, Thailand, parts of China, India, are dependent on runoff in big rivers, and much of that runoff originates in the Himalayas. The big issue is perhaps less the loss of water as it is the change in the timing of when that water is going to come. Because as global temperatures go up, what we're going to see in the warm seasons is faster melting of those glaciers. There will still be rainfall and snowfall in the high elevations, but the runoff is going to happen faster. And when you have a city that's dependent on runoff of a certain timing, or they manage the dams that are there to provide storage in the wet season so they can use it in the dry seasons, it's going to be a very severe challenge to those cities. There may well be supply problems, but there absolutely will be problems with the management and the timing of runoff. We're likely to see much more severe flooding,
right? Because
we'll get rapid melt from the glaciers even during the monsoons, rather than storage of some of that as snowfall. Much more damages, probably serious water quality problems, and maybe almost certainly some water supply problems as well. And we're trying to figure out now where the worst impacts are going to hit.
Yeah, I understand that it's actually kind of you get in the situation where you actually end up with more water because the glacier is melting, And so you're getting the regular water plus the melting, and then of course you get to the point where it melts too much, and then all of a sudden, boom, you're out of water.
Yeah,
But
that's a good point. Well, there will be an increase in flows in the short term as those glaciers melt, and then that water is lost, and that's the long-term water supply concern.
And isn't that happening already in places in South America? Like the smaller glaciers and the Himalayas, obviously.
Yeah, we're losing ice on every land surface, and in the Andes, the high altitude glaciers are losing water. We're losing them in the Rockies. We're losing them in the Himalayas. It's one of the clear hydrologic impacts of global warming is impacts on ice conditions. And that has positive positive as in bad feedback effects on the climate. As we lose ice in the Arctic, the Arctic becomes more absorbent of solar energy, less reflective, less sun is reflected, and that's a positive feedback. It warms even faster, and that's a positive bad feedback. And yes, we're losing ice in the Andes, and that's affecting water supply in parts of Argentina and Chile.
Yeah. And then also, besides sort of these specific situations, in general, we're also shifting weather patterns. My understanding is that the Sahara Desert is moving north into Southern Europe. And I mean, and this is something that's not like some just future thing. The conditions are already changing in, for example, Southern Europe in terms of water supply and elsewhere around the world. Can you just talk a little bit about shifting climatic conditions and how that relates to water?
Yeah, so this is, of course, a fundamental characteristic of human-caused climate change, is the shift in the climates and ultimately the day-to-day weather that regions experience. As temperatures go up, we're seeing these changes in the hydrologic cycle, and that is affecting who has how much water and what the temperatures are. And so climate zones are shifting. We already see that, even in the United States. I forget the organization that puts out estimates of vegetation zones to help gardeners plant things, and vegetation zones are changing. It's warmer everywhere. It's drier in some places and wetter in other places. And the plants that we planted in one place, or the natural ecosystems that evolved in one place, find themselves being displaced. Tree lines are moving north. Vegetation patterns are moving north. Hydrologic systems are fundamentally changing. And so if you think about it, all of our infrastructure, all of our water reservoir systems, the way we manage our water systems, they were designed and built for the climate of the 19th century and the early 20th century. They were designed and they were built and they're operated for a climate that no longer exists. And in the water world, that's already leading to big disruptions in the way we have to operate our reservoirs, the way we're dealing with ice patterns and ice melts in the Himalayas that we've already talked about. It's disrupting our institutions and our infrastructure.
So before we get into the solutions part of the discussion, we see the global temperature is, according to Jim Hansen and others, it's accelerating upwards. Last 2 years have been much warmer than what expected, by the way, and much warmer than ever before. And I understand, by the way, sea level, I just read the other day that sea level rise last year was significantly higher than the average sea level rise because water expands when it heats up. The extra heat from the recent temperature rise has caused that to happen. But where else have you seen like dramatic changes in water because of this accelerating warming we've been having more recently? Have you, do you think the extreme precipitation, for example, has gone up a lot in the last couple of years? Are we seeing those like immediate impacts of jumps in temperature?
Well, we do have to be a little careful about short-term trends in this, but absolutely the rise in temperature in the last couple of years and the now accelerating sea level rise that was just reported is very worrisome. Climate modelers try to be cautious, and there may be some indication that our climate models are a little too conservative, that in fact climate change is going to accelerate at the extreme end of what these models suggest, the extreme bad end of what these models suggest, rather than the median or the low end.
That's
I
right.
think we have to be pretty careful. We have to keep an eye on that.
Mhm.
Part of the big jump in temperature last year might have been associated with a reduction in aerosols. We're trying to reduce aerosol pollution. Aerosols cool the planet to some degree. And we've been pretty successful in the last couple of years in taking certain kinds of aerosols out of the equation. Maybe that will slow down again now that those are out, but maybe it'll accelerate. Big changes in clouds. We don't understand clouds very well. And on the hydrologic cycle, it's hard to say that the recent acceleration has necessarily caused a change in some of the water statistics that we've seen, but we have seen a change in hydrologic conditions over the last several decades, and that continues, and it's going to get worse.
Mhm. So let's talk a little bit about solutions. One that I guess everyone thinks about is desalination. And there's some pros and cons to that, but maybe you could walk us through whether you see that as a viable solution for many parts of the world. Is it going to be just more limited? Obviously, you want to be near the ocean, but besides that, what are your thoughts on desalination and the role it can play?
Save the desalination question for a minute, because I may not come back to it. Let me frame the solutions thing first. This is a classic. I'm sure many of the people you've had on have already talked about this. But the famous way of thinking about solutions is we have three choices: mitigation, adaptation, and suffering. And the question is, what's the relative proportion of those things? And that's true for greenhouse gases and climate change. It's also true for water resources. We have to mitigate, we have to reduce emissions of greenhouse gases and mitigate the consequences. There is a water component to that, because water and energy are very closely connected. It takes a lot of energy to collect and treat and distribute and use water resources, a major amount of energy. And so if we can think about our water system and the energy required to run it, and figure out ways of reducing the energy demands for water, that contributes to mitigation. That's a positive strategy. And so I'll give you a silly little example, but it turns out to be important. In the last couple of decades in the United States, we've implemented national, first state, but then national regulations on the energy efficiency of appliances.
Correct.
Refrigerators, dishwashers, washing machines, toilets, that kind of thing. We've also included water regulations, restrictions on the water requirements. So our washing machines and our dishwashers and our toilets are much more water efficient today than they used to be. So we're meeting our demands for clean clothes and clean dishes and flushing our toilets with less energy and less water. And that's reducing the greenhouse gas emissions associated with that part of the water system. So that's an example of water and energy mitigation. We're thinking about energy and water together. That's an important part of it.
So speaking of that, one of the things we've talked about here on Climate Chat is the fact that there's something called the rebound effect. When you, for example, lower the fuel efficiency of cars, people drive more, they drive more alone instead of with others. And of course, with the money they save, they take a trip to Spain. So in reality, for things like energy and computational energy efficiency, the Jevons paradox seems to apply. And the phrase is, and this is why I want to get to water, the more efficiently you use a resource, the more that resource is used in total. That's Jevons paradox. Does that apply to water? I can imagine water efficient appliances leading to more people moving to Las Vegas and Phoenix and things like that as well.
So I have very strong feelings about the Jevons paradox. It's partly crap. It's partly wrong. It's partly misunderstood. There is in some sectors and for some things, a little bit of a rebound effect where you save some sort of a resource with an efficiency improvement, and that resource just gets put back to use. But if you think about it properly, if you think about the productivity of our energy use or the productivity of our water use, there is still an improvement. And let me give you there are lots of examples in the water area. When you replace a 6-gallon per flush toilet with a 1.28 gallon per flush toilet, which is the national standard, the amount of water required to do what you want to deal with your sanitation problems goes down by 75 or 80%.
Yeah.
And we don't automatically then take that savings and squander it in our households. The Jevons effect doesn't apply for that kind of efficiency improvement.
Right.
When a farmer stops using flood irrigation and uses drip irrigation and produces the same amount of food with less water, that's an improvement in efficiency. Now, it's possible that the farmer will take that saved water, and if he has land, he'll increase the amount of land he uses that water on. And so the amount of water used actually doesn't go down. Some people say that's the Jevons effect, but I disagree with that. Because what's happening in that case, and it doesn't always happen anyway, is that the farmer is producing more food with the same amount of water. He's being more efficient. He may have expanded his irrigated acreage, and it's hard for farmers to do that. So in fact, most farmers, when they improve irrigation efficiency, that water is actually saved. And some other farmer may use it or may go restoring ecosystems, but it's a true improvement in productivity of the water use productivity. So sometimes there's a rebound effect, but it's absolutely essential, which is my key point, that we improve the efficiency of what we're doing, that we reduce the resource use required to do what we want, the energy use to do what we want, the water use to do what we want. If we can improve efficiency, we can reduce our impact on the environment.
Yeah, I think water is interesting because it is like a finite resource for many regions. And therefore, like in California, let's say, so if a farmer does use less, of course, he has incentives not to, which is kind of a whole California thing. But if he does use less, then other farmers will grow. But you're going to still hit that limit of the total availability. I think it's different in energy, where we create more and more energy, or computation. We certainly can create more computation, and Jevons really seems to have an impact there. But I also agree with you that you're going to get more food, and therefore you're also going to get more people, and therefore you're going to get more demand for water and food. And so you're going to get these things are intimately tied together as a system, and the long-term impacts of that system being more efficient probably plays out in different ways.
Okay, well, let me give you another great example.
Okay.
I didn't bring any slides to show, but this is my favorite slide when I give these talks.
Okay.
There's always been an assumption that as population grows and our economy grows, our demand for resources will grow. That's fundamental to planners, to resource managers, to sort of everything. And if you look at the gross domestic product of the United States, goes up exponentially. That's what economists like. We can have a conversation about whether that makes long-term sense or not, but that's what economists like to see. Our population of the US has gone up. Water use in the United States from 1900 to about mid-1970s also went up with population in the economy. And then something happened. And in the mid-70s, we split those curves apart. And today, in the United States, despite the fact that our economy is much bigger and our population is much bigger, total water use for everything has gone down. It's below
in absolute terms,
terms and per capita terms, but in absolute terms, we use less water today for everything than we used in 1980. It's a great example of the improvement in efficiency and the way we manage water and the failure of the Jevons effect. It hasn't happened. And there are lots of reasons for that, but people don't understand that. The assumption is still, our population's growing, our economy must be growing, our demand for resources must always be growing. And that's not necessarily true. And it's a paradigm shift of incredible import. And it's very positive, in my opinion.
That sounds great. Yeah. Again, I think Jevons is more for the things where you would take an unlimited supply if the price was low enough. And that's not necessarily true for water. I mean, once you took your shower and you used the toilet and whatever else, you wash your clothes, you don't want to like wash your clothes 5 times or something because there's more water available.
Yeah. And of course, in water scarce areas too, we have limits. You could say, well, I'm just going to grow a bigger garden. I'm going to spend more water outside.
Hmm.
But where they're in the Western US, for example, we're already pushing really hard on outdoor landscape efficiency and getting rid of
And
lawns,
getting rid of it. Yeah.
getting rid of lawns because we're up against limits and we're trying to restore ecosystems as well. That's the adaptation side. We had talked a little bit about mitigation, but there are lots of things to be done on the adaptation to climate side as well.
Well, for water, what are
For
some
water.
of your favorites besides besides limiting watering for gardens or lawns and things like that? What else should
So it
we be
partly
doing?
depends on what the impacts are on water systems, and then we have to adapt to them. So if we're talking about coastal flooding and big storms, you either protect the coast or you abandon the coast. You stop building in floodplains. That's a long-term adaptation. For water demand, improving the efficiency of water use, reducing the amount of water required to do the things we want in agriculture or industry or our homes, is a tremendously important adaptation step. If there's going to be less water, then reducing the demand for water to do what we want is a really helpful adaptation. Another one is, we're up against limits of supply. We can't have any more water out of the Colorado River. We take it
Right.
all. We're already overdrafting groundwater in the Great Plains and
Hmm.
in the Central Valley and in China and India. So we want to grow more food with less water to adapt to those kinds of things. So instead of looking for new supply, if there isn't any more new supply, let's find alternative sources of supply. We collect and treat a tremendous amount of wastewater. We typically treat it to a very high standard in the United States. And
Hmm.
then typically we throw it away.
Right.
If you're on the coast, we dump it in the ocean. Well, we can treat that water to any standard we want, and it's a reliable source of new supply that doesn't require killing our rivers or overdrafting groundwater. In California now, we treat and reuse about 18% of our wastewater, and we're talking about tripling that. Singapore collects and treats almost all of their wastewater, and they
Hmm.
treat it to such a high quality that they can use it for their chip manufacturing, which requires ultra pure water. So that's an
Hmm.
adaptation. That's another adaptation. And back to your question a few minutes ago about desalination, we know how to take salt out of water.
Yeah.
97% of the water on the planet's in the oceans. It's salt. Water's too
Mhm.
salty to drink. It's too salty to use to grow crops. But we know how to desalinate.
Correct.
It's expensive. It's technologically intensive. It has some environmental challenges. It's a source of last resort, in my opinion. You have to do
Mm.
conservation and efficiency and wastewater treatment and reuse and better stormwater capture first. But it's available to us if we're willing to pay the costs and we do these cheaper, smarter things first. And they're doing a lot of desalination in the Persian Gulf and the Middle East. We have one big desalination plant in California at Carlsbad. So
Mhm.
that's also an adaptation option.
Okay. Well, what about some of this one that people might not know about, but it's kind of an interesting for a certain situation, taking water out of the air.
Yeah.
What are your thoughts on people might not know? You can buy these they look like solar panels, and they actually have some solar panels on them, but they're taking water out of the humidity in the air and giving you liters per day. This is not large amounts, but enough to drink, for example, and maybe do some things. What are your thoughts on that as a technology that's going to make a difference, or is it just more a curiosity?
Yeah. So, anybody who has an air conditioner and lives in a humid environment will recognize that sometimes you get a lot of water out of your air conditioner. It actually cools the air, and as it cools it, the water condenses. And it turns out that if you concentrate on that technology, if you design for that, that in humid areas where there's a lot of moisture in the air, you can build machines that will explicitly that use energy, quite a bit of energy, it
Right.
turns out, to take water out of the air. Um, Again, I think this is a technology of last resort. It's incredibly expensive, more
Mhm.
expensive than desalination. It's very energy intensive and technology intensive. It's only really good in places where humidity is pretty high. It's not very good in desert areas because there's not a lot of moisture in the air. But again, they're using it in some places. They're testing it. The price is coming down a little bit. Um, so I think it's one of the things we keep in our portfolio of solutions, and where other options aren't viable or where this one seems particularly possible. I think it's an option.
Okay. And Speaking of a little more unusual solutions, but one that's been discussed forever, I don't even know what the current status of it is, but cloud seeding, sort of getting rain when we want it as opposed to when nature wants to give it to us. What is the reality of that today, and where do you see it going in the future?
The scientific community is mixed about the effectiveness of cloud seeding. The idea basically is when you have clouds, you can artificially inject very tiny particles that help condense the water and make it rain sooner than it would otherwise rain. We did some cloud seeding for a number of years in California. They do some cloud seeding in other places. There is some suggestion that it might increase rainfall in a particular area by a few percent or 5 or 10%. Of course, you're taking out water that might have fallen on your neighbor's territory. And so there's sometimes some political opposition to cloud seeding. And I think it's just not all that effective. Again, it might be something we pursue briefly in a few areas. They're starting to do it in parts of the Persian Gulf, but I think it's never going to be a big part of the solution set.
Okay, and I don't know if you've looked at this, but one thing we talk about on Climate Chat a bunch is solar radiation management, solar geoengineering, which would help cool the planet. I'm pretty confident that would be true because it's like a big volcano going off every year. But it would also impact water systems. Have you looked at that at all, and have any thoughts on how solar geoengineering might affect our water situation?
I'm not an expert on this. There are tremendous, as I know some of your previous guests have discussed, uncertainties and worries and risks about solar geoengineering. We certainly don't want any intentional geoengineering to reduce the pressure to do the right thing first, which is reduce greenhouse gas emissions.
Right.
Some of the fossil fuel companies are saying, "Oh, let's just solar geoengineer our way out of this, so we can keep burning fossil fuels."
Well, that's not, yeah.
That would be wrong. But some of the consequences will certainly be on the hydrologic cycle, and I don't think we understand them fully. And long before we launch any solar geoengineering effort, we better understand what the many different consequences will be, not just for temperature, but for water resources, for all sorts of other secondary impacts.
So I mentioned a few water solutions, but there's probably many other. What are some of the other solutions that you look into, or you think that are options for the coming decades to address water?
Yeah, so generally we want to build what we call the resilience of our water systems. That means we want to prepare for impacts that are coming. We want to harden the system so that they're less vulnerable to the consequences of climate change. We want to expand our ability to recover after damaging events occur. That includes insurance policies. So all of those categories have actions in the water area. And water utilities are beginning to think about those. We're looking for alternative sources of supply. We're reducing demand. We're trying to move vulnerable infrastructure out of vulnerable areas. We're changing the way we manage reservoirs. And we're trying to think about recovery after disasters so that when there are damages, we can return to normal. We can continue to provide safe water and sanitation for the populations that fundamentally need it after a disaster.
Okay, so a couple more questions before we move on to the audience and COMOD questions. But what policies? I know this is not a time to be thinking about what policies should be put in place here when policies are being destroyed. But we'll get to that too. But if you could sort of map out high-level policy, you just mentioned a lot of things we should be doing. But are there any sort of national policies that you think us or other countries should be implementing to deal with water in the longer term?
Sure. So there are many different pieces to the water puzzle, of course. The current destruction at the U.S. federal level of science and policy is I'll just say it explicitly, it's inexcusable. It's outrageous. Hopefully, it will be short term. One of the advantages of water is that water is often a local issue. So there are a lot of things that can be done at the local level. Our water districts are locally managed. There's a lot that can be done at the state level. There's a lot that can be done at the international. If the U.S. federal government is going to abdicate on its responsibilities to protect us, we're going to have to find other ways to deal with that. If you worry about violent conflicts over water resources, which is one of the things that I work on water and conflict,
Right.
including the role that climate change is going to play at increasing the risk of violence over water. You want international agreements about shared water resources. We have an agreement with Mexico, but on the Colorado, but many of the major rivers around the world don't have agreements among the nations that may share those water resources. And especially given the threat of climate change, it's urgent that we use diplomatic resources and develop international agreements on those rivers. So that's an international thing that we could do. Obviously, the Paris Agreement and other climate agreements are critical on the mitigation side. The more we can slow the rate of climate change, the more we can slow the impacts on everything, including water resources. And so we need to keep pushing, even if the US is not part of this. The global community absolutely needs to keep pushing on those things. And those are just some of the responses we need to make.
Yeah, I think of Pakistan and India sharing rivers that, both nuclear armed nations and things like that. That's just one of many scary areas of the world.
Yeah, there are lots of them. Afghanistan and Iran are fighting over the Helmand River. Turkey, Syria, Iraq, and Iran share the Tigris and the Euphrates. 11 countries share the Nile. We think of it as an Egyptian river, but all those countries are upstream of Egypt, and Egypt's sensitive.
And there a big dam being built, or was it's already done?
Very big dam on the Blue Nile in Ethiopia, the Grand Renaissance Dam. Egypt threatened violence over that, but Ethiopia went ahead and built it anyway.
So as climate change increases tensions for all other kinds of reasons, but water is maybe the one that's going to trigger violence the soonest.
We already see it.
Yeah, very, very scary. So you kind of answered the last question, but I was going to ask you a little bit about your thoughts on as you put it, the destruction of science in the United States. One of the things that made us a great country and a leader in the world, they're trying to tear apart. Any further thoughts on that beyond what you said?
It's dismaying. It's worrying. There's lots of historical precedent for this. Nazi Germany destroyed German science, and all the best German scientists fled and helped build American science. Stalin destroyed Soviet genetics for decades. There are just plenty of examples. Science is going to continue. Science helped build America and the strength of the United States, but other countries are going to step up, and American scientists are already starting to move abroad. Canada's offering American scientists positions. France is, the UK is. It's not as though Donald Trump is going to be able to destroy science. He's just going to be able to destroy American science and American universities. And if we let him do that, shame on us.
Yep. I agree with that. So now I'd like to welcome Stacy, our comrade, for her own questions, as well as those from YouTube.
Yes, and thanks for being here, Peter. I'm sure I have just a couple responses to things you said. I'm sure you must know about I live in San Francisco, and that we're trying to use our groundwater more. And I know that there are lots of put the water back in the land, like have little projects, to get water in the land. You probably inspired some. And then also about the Colorado River, why wouldn't they use percentages? Why wouldn't they take it back, say, okay, the treaty we signed on this day, we estimate that the allotment that was given to each of you is this. We're going to use it on percentages now, because you can't get water from the Colorado, blood from the stone, that kind of thing.
Oh, so two great questions. The Pacific Institute, my institute, one of the things we did recently is we did an analysis of the potential for capturing more stormwater in urban areas. It rains, and we built these water systems so that we can get rid of these big floods during storms so that they don't damage us. We're now thinking about capturing more of that stormwater in urban areas in California, but elsewhere. storing it in groundwater, as you've just described in San Francisco, and they're doing this in Los Angeles. We're trying to do it in the Central Valley for farmers to recharge overdrafted groundwater. That's an adaptation strategy as well. If we're going to get more intense storms, if snow is going to melt earlier from the Sierra Nevada mountains, we have to think about ways of capturing that water differently. And groundwater is a really important strategy. So that's a wonderful opportunity to talk about that. Your question about the Colorado is a great one. The agreement signed in the 1920s among the 7 states that share the Colorado gave different amounts of water to each of the 7 states. And it was different amounts. It wasn't a percentage of the flow. We assumed at the time, incorrectly, it turns out, how much water the Colorado would be able to deliver on average. And they were wrong in the 20s. Even without climate change, they overestimated, and they gave away more water than was available in the Colorado. And now with climate change, as we've discussed, that problem's going to be worse. If they had used percentages, the challenges today would still exist, but they'd be much less. There are negotiations now among the 7 states and between the US and Mexico about how to deal with these shortages. I don't think they're going to move to percentages. I think what they're going to do is figure out how each state will be shorted in terms of an amount. California will get a little bit less, and Arizona will get less, and Nevada, and we'll have to figure out within each state how those shortages then will be allocated among our own users.
Okay.
Gotcha.
Stacey,
sorry. Oh, go ahead.
Just before we go on to YouTube question, I'd like Eli to ask a question.
Sure.
Is that now the time? So hold on. Eli, welcome. And what's your question for Peter?
Hi, thank you, Dan. So one of China's adaptation strategies, though this probably would have happened on its own, is to massively scale up what are called caterpillar tunnels. Some people may know them as hoop houses in agriculture. And this increases the water utilization efficiency of agriculture because you reduce what you lose to evaporation. They've also noticed, incidentally, that just the polyethylene film is actually changing albedo favorably. So there's a little bit of a net cooling effect. I'm wondering if anybody has analyzed the effect of water savings, if those kinds of adaptation strategies could reduce the water demand of agriculture, on the widest scale possible, how much that would spare relative to what we expect to lose due to climate disruption type effects, to perhaps divert more to ecological restoration.
Yeah, so a great question. The agricultural question is really at the heart of the water challenge, and of course it's at the heart of the climate challenge. I don't know the extent to which that particular technology can be widely applied. It's useful for certain kinds of crops and certain kinds of soils and certain kinds of climates. But it's an example of the many different kinds of adaptations that farmers are starting to apply. The agricultural sector is fairly conservative. They're conservative politically, they're conservative economically. A lot of them deny the reality of climate change, but on the other hand, a lot of them understand that something is happening. And farmers really are smart, ultimately. They will figure out, given the right incentives, given the right information, given the right science, how to grow more food with less water and with fewer inputs. They have to be given the right signals. And so this kind of adaptation and some of the adaptations that I talked about earlier, precision drip and precision sprinklers, changing crop types. Maybe we shouldn't be growing alfalfa in the Colorado River region with irrigated water. A lot of the Colorado goes to that kind of water intensive crop. These kinds of adaptations are absolutely going to be vital at our ability to continue to feed the planet without destroying the environment. And as your last point was, potentially restoring ecosystem flows. We in the 20th century, we didn't understand or we didn't care about the impacts of our water policies on the environment. We do now, mostly, and we're starting to figure out how to restore ecosystem flows. And working with farmers to do that turns out to be an important strategy.
Okay, very good. Thanks, Eli. And Stacey, do you have
Oh,
questions
so
from the
many great questions. Yeah. And one thing I just wanted to note, you were talking about the Jevons paradox, which we talk about all the time, and the contradiction. And I was wondering, possibly the Jevons paradox, the way we always talk about it, Dan, might apply to human-made things, and that it doesn't apply maybe to natural resources. I don't know.
I think also things that are limited in the total anyway, and especially things that you don't necessarily use more of if they're cheaper. But anything that
Gotcha.
you use more of that's cheaper, like energy and computation, seems to really apply in those cases as well.
For sure.
So
So many
I
questions.
just really, I'm sorry.
keep going.
I just really want to emphasize that we cannot use the Jevons paradox as an argument for not improving the efficiency of our technologies in water use and energy use. What we do with the saved energy and what we do with the saved water is a policy question. If we're going to save energy by improving energy efficiency and then let it be inexpensively priced and let it be used somewhere else, that's a policy question. And it's true for water as well. If a farmer improves efficiency of water use and saves water, where that saved water goes is a policy question. And if we let it go back to restoring ecosystem flows, that's an improvement. If we let farmers expand irrigated acreage and use it on wasteful crops, that's a policy question. So we cannot dissociate efficiency from policy. And the Jevons argument often misses that point.
Well, no, actually, I 100% agree. In fact, the way around Jevons is exactly that, is that, if you want, if the efficiency improvement comes in response to, for example, a fee on carbon, then you've controlled it. But if you exactly the way you say it, if you just let it go, which is, by the way, what we do with computation, the computation's improved by 13 orders of magnitude since the 1940s, and only energy use has gone up, but there's no regulation on that. But so I 100% agree with the way you framed it there. That's actually a very important point. Let's see. I can pop this one up here. Watch this. We have a question on it that I was going to ask, and this is a new tech thing we can do with popping the question up, is what percentage or impact does animal agriculture have on water use or contamination?
Oh, another great question. So it's a big factor. Obviously, it's tied to everything we care about, but one of the things that we do in the water world is we calculate water footprints. We do this in the energy world as well, carbon footprints, which is the amount of water required to produce the goods and services that we want. And when we apply the water footprint calculations to agriculture, there is no doubt that the most water-intensive food is meat, and the most water-intensive meat is beef. So it takes like 15,000 liters of water to produce a kilogram of beef. It takes 1,000 kilograms of water to produce a kilo of wheat. Wheat and grain, much less water intensive than meats. And so from a climate point of view, or a water point of view, or a land point of view, meat intensive diets are very resource intensive. The diet question is an important part of the solutions issue that we ought to be discussing. And I'm glad the questioners raised that.
Very good. What else, Stacy, do you have?
There's how much fossil fuel does water treatment take?
Oh, another great question. I talked a little bit about the energy requirements of our water systems, but there are water requirements for our energy systems. And again, we've done a lot of work at the Pacific Institute on the energy water nexus. And it turns out one of the biggest demands for water in the United States, non-consumptive, but a big demand for water, is to cool power plants, thermal power plants, fossil power plants, and nuclear power plants. Now, most of that water goes for cooling. It's not consumed in the sense that it's used for cooling. It goes back in the river a few minutes later, a few degrees warmer. But there is also a consumptive use of water by fossil power plants. So anything we can do to get off fossil fuels reduces greenhouse gas emissions. Anything we can do to reduce fossil fuel use reduces water use as well. Renewable energy systems are much less water intensive than traditional fossil and nuclear energy systems. And so again, the renewables revolution has an important impact on our water use too.
As does the fake meat. That those sort of proteins take a lot less water than what animal agriculture does.
Right.
Yeah, let's do one more because we're getting
One more.
top of the
Okay.
hour.
Oh my gosh. Well, I mean, I have to. Leon asked a question,
Oh.
and that is, can you talk about shifting of the ITCZ? And since we're trying to avoid acronyms, that is the Intertropical Convergence Zone, a low pressure area near the equator where trade winds converge.
Yeah. So this is we talked about this a little bit about shifting climate zones around the world. The way the climate works is there are these Hadley cells that move moisture from one part of the planet to another, and they're in the northern hemisphere and the southern hemisphere. And sort of in the middle, it's sort of a calmer area. These zones determine when and where we get rainfall. The reason the Amazon is incredibly wet is because of where these zones are and these Hadley cells and these precipitation patterns. And one of the things, again, we really worry about on the water side from climate changes is big changes in where rainfall patterns occur. And we're already seeing, for example, drying in the Amazon. And part of that may be due to the deforestation of the Amazon, but part of that is due to these much larger scale climatic changes in the tropics in particular.
Another is, how will sea level rise and subsequent salt intrusion impact Florida's freshwater aquifers? Is it ruinous?
Yeah, so Florida is ground zero for a lot of the impacts of climate change. Vulnerable to hurricanes, vulnerable to flooding, incredibly low lying, dependent on limited water resources, mostly groundwater. It rains, it seeps into the porous aquifers in Florida, and that's where most of Florida's fresh water comes from. And as sea level goes up, saltwater intrusion to those aquifers is already occurring, and it's going to affect the water supply for big cities in Florida. It's pretty ironic given that Florida's government sort of denies the reality of climate change and is doing what they can to kill climate research and doesn't like to use the words climate change.
Right.
And yet they're really among the most vulnerable in the United States to some of the impacts we've been discussing.
And you see that happening in 10 years?
It's already happening. It's going to accelerate as sea level goes up, as storms go up. Those kinds of contamination events in coastal aquifers, again, it's already happening, and it's going to get worse.
Okay.
I wanted to fact check two things that I read in the chat that were like, whoa. One was that 80% of waste flushes into the ocean untreated.
So it depends on where you are. In the United States, we have the Clean Water Act, and the Safe Drinking Water Act requires that we collect and treat wastewater. We treat it typically, as I said, to a very high standard. And often, if you're on the coast, we throw it away because we haven't been reusing it. But it's typically pretty good quality water. But in much of the rest of the world, there are no comparable sophisticated wastewater treatment systems. Sewage flows untreated into the oceans. That's a serious water quality problem. And so we need to collect and treat all wastewater. And if we treat it to a high enough standard, we can reuse it. And that's an adaptation that we've talked about.
That's very okay.
And the other was that they said, I find it scary that big rivers no longer make it to the ocean. Is that true that some rivers aren't making it there?
It's true that some aren't. The Colorado River in an average year no longer reaches the Gulf of California. And it's consumed entirely by the 7 states and Mexico. In a really, really bad flood year, in a really wet year on the Colorado, which we're seeing fewer and fewer of, some flows of the Colorado might reach the Delta. The Yellow River in China in a few years ago started to go dry, and for hundreds of days each year, no flows would reach the China Sea. We're beginning to consume all the entire renewable flows of a lot of rivers. The Jordan River, shared by Syria, Jordan, Israel, and the Palestinians, no longer reaches, in this case, not the sea, but the Dead Sea, which is where the Jordan used to flow. It's entirely consumed, and so the Dead Sea is disappearing because it's evaporating. It's another example of the total consumption of some of the renewable resources on the planet.
I have a great final question, which is, which one is it? This is how low do freshwater supplies need to drop in order for it to no longer be just a political problem, but a survival problem?
Well, so I worry less about that in the sense that every region of the planet, with very few exceptions, have enough water for basic human needs, which are very small, for survival, for cleaning, for cooking, for sanitation. I define those as 50 liters per person per day in a paper I wrote in the 90s. The UN, there's some discussion, 25 liters a day, 50 liters a day. That's a very small amount of water compared to the amount of water required for industry or especially agriculture. In an emergency situation, we can move basic supplies to prevent people from dying of thirst. People don't die of thirst. They die of water-related diseases. They die of fighting over water resources. They die of other things. But the biggest concern is growing water scarcity to meet the larger demands for growing food for people, for our industrial needs and for our commercial needs.
Very good.
Thank you.
So thank you, Peter. Thank you so much for sharing your insights with us. Any final thoughts you have for our audience in water?
Yeah, so I would say I always like to end this way. I am an optimist. In the book, The Three Ages of Water, the third age is my vision for a positive future for water. And it's based on the fact that there are solutions to all of these problems, just as there are solutions to the climate problems. I think ultimately we'll move to a sustainable future for water, but I don't mean to minimize the bad things that are going to happen between where we are today and where we want to be. The challenge is to see what's successful, see what's working, scale those things up and make them happen faster. This is true for water, it's true for energy, it's true for climate, to reduce the bad impacts that are coming and to accelerate our transition to a positive future. We sort of know what we need to do. If only our politicians and our traditional bad infrastructure and institutions got out of the way, we could do those things faster.
Great. Well, it's a great note to end on. And by the way, there are links in the description to Peter's website, and it will also take you to his book. And so you can learn more about all the things we talked about today there. There's a lot of great information on his website, by the way. So check that out for sure. Peter, thank you again for joining us again. Really appreciate it. And thanks to everyone for joining us today. And we will see you next time, which, by the way, for those paying attention, will be tomorrow morning with Leon Simons hosting Vincent Gauci, talking about the rise in the temperature leading to more methane. Cleaning air pollution leads to more methane, which is everything's interrelated in this world. Thanks, everyone, for coming. We'll see you next time. Bye-bye.
Thanks very much.
Bye-bye.